Welcome back to part 3 of the Introduction to Laplace Transforms. And we just got done talking about the gamma function, and notice that the gamma function of n plus 1 is n factorial. So the gamma of 4 was 3 factorial. We can now take the gamma function and use him to help us find the Laplace transform for t to the 8th power. Okay. So the Laplace transform for t to the a is, of course, by definition, the integral from 0 to infinity of e to the negative st times t to the 8th power dt. And if we do a u substitution where u equals st, so t equals u over s, then du would equal s dt. And if we use this u substitution and plug it in here, we can convert into this integral. So, and that's okay. We can even keep the limits because if s is a positive number, when t is 0, u will be 0. And when t is infinity, u will also be infinity. And when we get this guy will turn us into the gamma function. And so this will be the gamma function of a plus 1 over s to the a plus 1 power. So there was our u substitution letting u equal st. So combining them all together, the real meat to this story here is that the Laplace transform for t to the a is gamma of a plus 1 over s to the a plus 1. Now, if a is a integer, positive integer, this is really nice. For example, the Laplace transform for t to the first power, notice how a here is 1. So gamma of 1 plus 1, which is 1 times 1 factorial, which would be s over s squared. And so we would get 1 over s squared, like we saw on the first page with our definition of the Laplace transform. Similarly, the Laplace transform for t squared, we're going to get gamma of 2 plus 1 over s to the 2 plus 1 power. And gamma of 3 would be, careful, it's not 3 factorial, but 2 factorial. And 2 factorial is 2. So the Laplace transform for t squared is 2 over s cubed. Okay. Now I want you to try it for the Laplace transform on t to the 5th. And we'll even pause the video while you do that. All right, so using our formula here, we notice that a is equal to 5. So the Laplace transform for t to the 5th is gamma of 5 plus 1, 5 plus 1 is 6, over s to the 5 plus 1 or 6th power. And remembering that gamma of 6 is going to be 5 factorial, and 5 factorial is 120 over s to the 6th. Now, what if a is not a positive integer? It's not a square, a fifth, or a 23rd power. What if he's raised to a fractional power? Well, we can still use this, but we have to know one more thing. I'm not going to prove this, but gamma of 1/2 is the square root of pi. So let's try it. So let's try the Laplace transform on t to the 3/2 power. Well, to do that, we're going to do gamma of 3/2 plus 1, which is 5/2, over s to the 3/2 plus 1, which is 5/2. And remembering our definition of what the gamma, or well, our relationship on the gamma function, we're going to get that gamma of 5/2 is going to be 3/2 times gamma of 3/2, and it's still over s to the 5/2 power. Doing it again, gamma of 3/2 is going to be 1/2 gamma of 1/2. And we know that gamma of 1/2 is square root of pi. And so these two multiples out here, 3/4, square root of pi over s to the 5 halves, which occasionally is written as 3 square root of pi over 4 s to the 5 halves power. So what I want you to do now is try the next one. Let's try the Laplace transform of t to the 5 halves power. Pause the video and give it a try. Let's see how you did. So we just follow our pattern here, our formula that we've developed. Laplace transform of t to the 5 halves will be gamma of 7 halves over s to the 7 halves. But then we use our relationship on gamma of x plus 1. So that will be 5 halves gamma of 5 halves over s to the 7 halves. And we whittle him down kind of like we did up here with the factorial. But we don't end up with 1, gamma of 1. We end up with gamma of 1/2, which is the square root of pi. So it should turn out to be 15 square roots of pi over the quantity 8 times s to the 7 halves. Okay. Now, these Laplace transforms get used quite a bit. So you will see on page 581, and actually in the front cover of your book, a table of Laplace transforms. And something really cool about the Laplace transforms, something that's really necessary and what actually makes it work, is the fact that Laplace transforms are one-to-one. Therefore, they have inverse Laplace transforms. And that's the important thing there is we need the inverse Laplace transform so that we can go backwards and convert from, kind of like our computer converted from base 2 back to base 10 so that we as humans understand it. Okay. So the table of Laplace transforms is also a table of inverse Laplace transforms. So the Laplace transform of 1 is 1 over s. So the inverse Laplace transform of 1 over s is 1. Similarly, the Laplace transform for, let's do, how about t squared? We did him just a minute ago and found out that that's 2 over s cubed. Therefore, the inverse Laplace transform of 2 over s cubed would be t squared. Now, sometimes we end up with something like the inverse Laplace transform for 1 over s cubed. And what we do is we recognize, hey, that's similar to somebody I do know. So let me write this as the inverse Laplace transform of 2 over 2 times s cubed. Notice how I've multiplied by just a 1, 2 over 2, which I can then say, hey, I know the Laplace transform of 2 over s cubed, so I can factor out the 1/2. So 1/2 inverse Laplace transform of 2 over s cubed, which would be 1/2, and the inverse Laplace transform of 2 over s cubed we know to be t squared. So here's how we can use that together with the linearity of the Laplace transform to find inverse Laplace transforms. Okay. So let's go ahead and do another example here. So we know that the Laplace transform for sine of kt is equal to k over s squared plus k squared. Okay, that guy's in your table. You can also prove him using the definition of the Laplace transform. So if we wanted to find the inverse Laplace transform for this guy, 3 over s squared plus 4, we recognize that he looks a lot like this guy, but the top, 4 is 2 squared, so the top would need to be a 2, not a 3. So let's times top and bottom of the fraction by 2, and then group it so that we've got somebody that we can handle here. And then we can factor this out, so this is going to be 3/2 times the inverse Laplace transform of 2 over s squared plus 2 squared, which then gives me 3/2, and this guy fits that same formula here, so this is sine of 2t. And as we've mentioned earlier, not every improper integral converges. So for the Laplace transform to converge, we need the function to be of exponential order. And we need the S value to be such that it will converge. So, and another thing that you should notice with our Laplace transforms that we've done here, the several ones, the limit as S approaches infinity of any Laplace transform is 0. Okay, so that's a quick check to make sure you didn't goof anything up. And that's 10.1 Laplace transforms.